Yeah. So I think preparing this talk, I realized how many details are still a little vague for me. So I do welcome questions, but I might not be able to answer everything. All right. So John Wentworth got into a bit of a kerfuffle on Twitter because somebody asked him what abstraction should be. And he said, well, probably eventually it has to do something with category theory. And then he said, but nobody understands category theory. Maybe you've seen it, maybe not. Before I explain, let me read this out. So the central dogma of Wentworth's agenda is the natural abstraction hypothesis. So that really has two parts. Let me read. Our physical world abstracts well. For most systems, the information relevant far away from the system is much lower dimensional than the system itself. These low-dimensional summaries are exactly the high-level abstract objects and concepts typically used by humans. Maybe approximately exactly. These abstractions are natural. A wide variety of cognitive architectures will learn to use approximately the same high-level abstract objects or concepts to reason about the world. Now, this is just word fluff, but I assure you there is an actual proposal. Something like it should be something like sufficient statistics or generalizations thereof. Right. So back to the Twitter story. Yeah, he said, oh yeah, nobody understands category theory, and it's his interlocutor asked him, oh, but what about, aren't there these people that write books about category theory? And he was immediately dismissive of them because he said, yeah, they can't explain to me. They can't really explain it to me. And by which he meant they can't explain how a category abstracts or category theory helps you reason about a giraffe, abstracts about a giraffe. So, well, it's
Did he say that?
a little silly, but the more general point. Yeah. So
I didn't see that part.
his point. I mean, okay, I obviously disagree with the harping on category theory, but I think there is a point to be made that we'd like to understand abstractions in the real world. We'd like to take we'd like to understand how humans understand abstractions in the real world. And obviously, a giraffe is an incredibly complex, on the micro level, it's an incredibly complex physical system. But still, we have these very effective high-level summaries of them, which can tell us lots of things. Not everything, but lots of things. It's not just going to dissolve immediately. It's probably going to walk. You give it food, it will sort of do conditional on it being hungry, it will eat it. These kind of things. All right. So the sort of test bed or the original ground of abstraction is, of course, thermodynamics. And so from this perspective, thermodynamics has nothing to do with physics, or it has something to do with physics, but it's not immediate. The direction isn't immediate. It's really a form of abstraction, information theoretic abstraction. And it just happens to be that some physical systems that we call gases or similar systems abstract well. Not all systems abstract well, but these systems do. All right. And there's a single principle that is often remarked to be the sort of central principle in thermodynamics, which is the principle of maximum entropy. So let me read it. So given constraints,
do you mind if I put the sign that's missing in your definition of entropy?
Functions of the system?
You're missing a minus sign there.
Oh dear.
Minus.
Yeah. What?
Can I just ask as well? Are you saying thermo, not thermo?
Right. Yeah.
Okay. What's thermodynamics? Sorry.
Thermo. No, they're
there's only
thermodynamics.
There's only one word in this vicinity.
Northern hemisphere sphere, southern hemisphere.
Okay. Thank you.
Yeah.
Thermodynamics, mate.
So given constraints, typical constraints will be expected value have to be fixed. Then the probability distribution which best represents the current state of knowledge about a system is the one that maximizes this Shannon entropy, satisfying the constraints. All right, well, here something went a little wrong, but I'll continue. The maximum entropy principle is one among a small set of normative rationality principles, or normative reasoning or decision principles. I find these very interesting, but obviously they come under criticism a bunch of times. One has to be a little careful about how and where to apply them. All right, so thermodynamics is really about coarse graining. We have microstates. We have this function that sort of forgets most of the details and sends it to a much simpler state. And usually we call these macrostates, but really you could have multiple layers of this. You could have these hierarchies of coarse graining. And some systems, typically ergodic systems, will be able to use the maximum entropy principle to basically derive everything that is important about them, or what is not everything that is reasonably recoverable from them. Or you could say the macros, if you pick the right high-level summaries, then these really pin down the system very well up to the fundamental uncertainty. So obviously ergodicity means space average is the time average. You could think of these also as systems in terminal equilibrium. Well, all right, maybe that's okay. I said the wrong thing. Let me just continue. All right, let me now give an example of how to use the maximum entropy principle. So let omega be the interval A to B. What distribution gives the maximum entropy? And the answer is going to be, of course, a uniform distribution, but we'd like to prove that. So the continuous case, the uncertainty given by HP. So just a question, do you see my screen, or how does that work again?
You want to write on the... if you want to highlight something, click
No, but if I click on a screen...
If you click on a screen, you only see that.
We
keep seeing whatever we're looking at, but if you write on it, we'll see it, of course. Yep, so we see that.
If you click on all...
So now you see the screen?
You can't affect what we see.
So now you see the...
So we see what you're writing, but...
Okay, so I don't... All right, then I'll just continue reading. So for the continuous case, uncertainty is given by the integral instead of the sum. Okay, very simple. And we want to find the function px that maximizes this entropy, the Shannon entropy, subject to the constraint that the total mass of the probability distribution is 1. All right, and we'll proceed by Lagrangian optimization. And here I realized that I was confused. Usually with the integral, and then you have to do something with like a functional derivative. I got lost in the basics. The Shannon entropy plus lambda, so that's the sort of free variable or conjugate variable with the constraint px minus 1. And you differentiate with respect to px, so you set it to 0. So it's minus log px minus 1 plus lambda. And then we derive px is e to the lambda minus 1. And so what you would actually probably would have to do is you have to differentiate again to get the second derivative and then show that it's a maximum. But I'm going to not do that. I think it's going to be fine. All right, we plug in the px is e to the lambda minus 1 again in the integral. 1 is a to b p of x. And then we solve for lambda. Then we get lambda is 1 minus log 1 over b minus a. And therefore, you can just put that in again. Px is e to the 1 minus lambda. You plug it in, you rewrite it, and indeed, you get the uniform distribution on a to b as expected. Okay, cool. All right, so we'll do another one. So we have a random variable with a fixed mean and a standard deviation sigma on the real line r. Right, so, oh, did it drop? Okay, well that's, sorry, I think yeah, the Lagrangian isn't right. The Lagrangian function, I guess, isn't right. Hold on, maybe the second slide. Okay, anyway, on the second slide, it is correct. So the Lagrangian function is minus px log px as before. The lambda 0 gives the same constraint. And now lambda 1, we want to fix the standard deviation. And because the standard deviation sort of implicitly
I don't understand this, to be honest. I feel like maybe I'm going to ask this question.
Yes.
And maybe you won't answer me, maybe. But how am I using a Lagrangian? I mean, that looks like I'm fixing px to b1, not the integral of px to b1. So how is this setting the integral to b1?
Yeah, I agree. Yeah, this is one of the things that I couldn't figure out last night. Yeah, I think what you have to do is you take the integral, then you take the functional derivative, and then it's going to come out as right. Anyway, I got confused. But okay, the thing
so yeah, this is a density, and then you integrate both sides with respect to x. So
so I called it not the Lagrangian, but the Lagrangian function, which I kept ambiguous. So I'm also confused about why you actually only need one constraint, because it's not super clear to me that it's enough. Yeah, well, the other thing with the integration, yeah, well, let me think. Yeah, anyway, that's right. Anyway, so we differentiate lambda with respect to px. We set it to 0. We get px to be e to the lambda 0 plus lambda 1 x minus mu squared minus 1. So sort of in general, these things will look like this. And we have these two constraints. So the normalization constraint gives, well, you plug it in, it's 1. And there's some algebra that isn't super insightful, but obviously you have to, you're going to, you're going to use that e to the x minus x squared is the square root of pi, right? The integral from minus infinity to infinity. Yeah, what more to say about that? Not so much. And similarly, with the sigma squared constraint, you can also calculate this kind of a similar trick and change of variables. and then I get e to the lambda 0 minus 1, is going to solve. Hold on. Wait, shouldn't I get lambda 1 here? I think should get lambda 1 here. Because otherwise... no, the other doesn't have lambda 1. Yeah. Okay, no, this is fine. All right. And you can plug these in, and you'll find that... why? Yeah, the lambda 1 is already solved out. So I have a constraint from above. Anyway, I don't know. It's not super maybe interesting. And you plug it in, and you get the famous Gaussian distribution. So that's px is 1 over sigma times the square root of 2 pi, and exp of x minus mu squared over 2 sigma squared. Yeah, so I think you'll sort of get this. You will get a Gaussian if you you fix the mean, or whether you vary it doesn't actually matter.
Okay, yeah, I follow this calculation now. I missed the lambda 1 in the denominator in the first equation on the left, but when you substitute
me too.
When you sub all that in, you do get that. Yeah, all right.
All right, so now we get to exponential families, and the basic setup now is, well, we fixed in the maximum entropy story. You fix the expected value of some measurable function to be a constant CI, and the I guess I called them lambda before, but yeah, now I called them beta for coolness, coolness parameters or inverse temperature. And now we can do sort of a second step, which is we can look at the family of max entropy distributions we get as we vary the constant CI, or we vary the constants, the coolness parameters beta I. And these will typically form nice families of parametric distributions called exponential families. And you can think of these as maximum entropy families. Sorry, you were laughing?
No, the first time you said coolness, I thought it was just because you thought they were cool. And then I realized it was actually a formal term. So I was chuckling.
Yeah. No, I jump by has been sort of, it makes total sense. Yeah. All right. So let's see what John Wentworth has to say about sufficient statistics. Because that's where we want to go. Right. So we'll see that these exponential families are very sort of canonical families. They arise from the maximum entropy principle, and they have these key variables, and usually they're given in the conjugate form. So you get these conjugate variables, these coolness parameters. And do I have to say more? No. Well, anyway, and these will be approximately the sufficient statistics. So suppose we want to estimate the mean and variance of a normal distribution for some samples x1 to xm from the distribution. So implicitly, we here we have a family. We're really doing statistical estimation for a family of normal distributions with varying mean and variance. It turns out that we don't need to keep around all of the data. Only the sample mean, mu hat, is the sample mean, and the sample variance. So he writes 1 over n, but I think there's this thing where sometimes you have to take 1 over n minus 1, and yeah, I think that's the better one, but I was a little confused, are needed for the estimation problem. From those, we can calculate the entire posterior distribution of mu sigma. Right, so if you have a, let's say you have a Bayesian statistics question, right? We have a family, we have a prior distribution on the family of normal distributions with varying mean and variance, and then we then we basically want to do Bayesian updating. It turns out we only need the sample mean and the sample variance. That's all you really need. So the pair mu hat and sigma hat is a sufficient statistics for x1, for the sample x1 to xn, a statistic which summarizes all the estimation relevant information from the data. So statistic, I think, is just measurable variable. I don't think or measurable variable of the sample, as far as I understand. In principle, every estimation problem has a sufficient statistic. Just let the summary be all the data. But this isn't very useful. We really want to compress the data, pull out the actually useful parts, and throw away the rest. In the normal distribution example, our n samples of data are each one-dimensional for a total of n dimension of data, but the summary is only two-dimensional, no matter how large n grows. All right. All right, so let's maybe a little more formal. So a statistic is sufficient, Tx is sufficient for underlying parameter theta if the conditional probability distribution P of x is x, given Tx of the data x, given the statistic Tx, does not depend on the parameter theta. So the sample mean is, for instance, sufficient for estimating the mean mu of a normal distribution with known variance. Once the sample mean is known, no further information about mu can be obtained, or I guess theta in this case. Mu is theta in this case, can be obtained from the sample x itself.
Yeah, maybe I would add here that the definition of sufficient statistic is not trivial, I would say. It takes at least I didn't find it trivial. I'm not sure I would have understood it just from this definition. It's, I think, a little opaque. But
is the definition incorrect, or?
Not incorrect, but I'm not sure that if you hadn't had it explained, it's possible to infer easily from this what that really means. I don't think we need to go off on a tangent and get into it. That's a topic for another time maybe, but I don't think it's... there are a few equivalent definitions, and I found it not... required a bit of thought to properly understand. So...
All right. All right. So let me continue with the KPD. All right. So the KPD theorem, Koopman-Pitman-Darmois theorem, it's not well known. It's an old theorem from the 30s. But yeah, I had never heard about it before reading about it in Wenworth's post. I don't know how much that says. I'm not no expert on statistics, but it's definitely a little obscure. So when will an estimation problem have a fixed dimensional sufficient statistic as the number of data points increases, like the normal distribution estimation problem. The Koopman-Pitman-Darmois KPD theorem says that when estimating distribution parameters from IID samples, there is a fixed dimensional sufficient statistics if and only if the distribution can be expressed in an exponential form. So yeah, I don't know, last night I confused myself with all the different ways to you can sort of write all these things. So I think this is the way, which is sort of writing it in this way. Yeah, so that's sort of the definition of an exponential family. It's a distribution, a parameterized family of distributions of this form. And as you can imagine, you can sort of wiggle around with a lot of the parameters and then get a slightly different form, and that's then equivalent. It's a little finicky definition. This is, as you can, the 1 over z should make you think of the partition function. Obviously, this is very close to sort of kind of everything that physicists do in thermodynamics, statistical physics. For some vector, okay, so it's expressed in this form. So you have the z there, you have the f, g, and h there. And so the f and the g are vector valued functions. And yeah, and you have a positive real valued function h. The h is not so important. But the g is. The sufficient statistics is then the sum over, yeah, basically it's the average, right? As in, yeah, so you take the sample, you have this function g, and you average it. So think about the sample mean or the sample variance, right there. In this case, g is the identity, or g is the x minus mu squared, and then you average it. Well, I guess you have to normalize it as well, or what is this called? Usually divide by 1 over n. For instance, for a normal distribution, yeah, okay. So the way this is like, I find this kind of confusing. So intuitively, the mu and sigma should be the sample mean and sample variance should be the sufficient statistics, but then you can sort of parameterize things. Obviously, if you multiply by some constant, that's not going to matter for an estimation. So all these things are not completely canonical. But anyway, intuitively it says the coupling between x and theta, so between the sample and the parameter space, is only via the fixed dimensional summary vectors f theta and the sum of g. Of the g. All right. So here you can also see a little bit better that the summaries for me, the sufficient statistics for the normal distribution is 2-dimensional. Both the mean and the variance can vary. And in a way that I find a little confusing, if you actually do the max entropy calculation, then somehow you'll only need to add 1 constraint, which I find confusing. I'm not quite sure how this works, or yeah. Well, if I say give me a distribution on R with mean mu and standard deviation sigma, then you write down the Lagrangian, but the Lagrangian only has 1 extra constraint. You don't have to add in the mu constraint, because somehow if you have the sigma constraint, then that implicitly pins down the mu. Yeah, I'm not quite clear on how this really works. Anyway, a lot of things weren't super clear to me. But let me say some things about the KPD theorem. Because to Wentworth, this is really one of the, key theorems, even though it's a little sort of obscure. Hold on, sorry. So from constraints using the maximum entropy principle, I get these distributions, and if I vary the constraints, I get these exponential families. By the way, Dan, are there other slides? I remember I put in other slides.
Oh yeah, there's one more over here.
They're around the corner.
Didn't quite fit.
Oh, okay. Are there not more?
These were all the ones you sent.
Okay. All right. Well, I'll just talk then. Yeah. So the just to finish my story about the KPD. So the as you vary the parameters, you get these very nice families. So from a sort of information geometry theoretic point of view, they're very nice. You can calculate their KL divergence in terms of these key sufficient statistic parameters. Then you get something. It becomes the so-called Bregman divergence. It's also sort of becomes more intuitive what the Fisher information metric on these families are. It's good that none of this is written down, so I would just only say it, and then you can tell me how approximately accurate it is. But I think if you take the family of Gaussian distributions with, let's say, varying sigma, and maybe varying mu as well, then right, and then also multidimensional. So you can have a multidimensional mu, multidimensional sigma. Then the Fisher information metric will sort of locally give you this correlation, the correlation matrix. Somehow in this correlation matrix, there's also the you can try to find the eigenvectors, diagonalize it, basically do PCA. So PCA is like a sort of special case of this story, and more generally, the way to find these abstractions, so the sufficient statistics, according to John, is like doing basically PCA locally. But I don't really understand how this works, but that's what he said to me. Okay, so one more thing about the KPD theorem. Right, so you start with the constraints, you let them vary, you get these families, you use the maximum entropy principle. So these are systems that...
so PCA locally has to refer to, the diagonalization of the sigma. Well,
of the sigma, maybe a Fisher information metric.
Yeah, that's right. So if you look at that exponential family and then look at the Fisher information metric at any given point, as long as it's non-degenerate, you'll be able to diagonalize it, and the PCA will be the vectors of the highest eigenvalues. But that will vary as you move around. More importantly, the places you actually care about, it will be degenerate. So PCA is actually not really a good way of thinking about this, but it's...
of course. I'm preaching to the choir here. Right, so the KP... So in thermodynamics, this sort of maximum entropy principle story works very well. Not all systems are abstractable in this sense. the fact that thermodynamics, these thermodynamic systems are like, ergodic, they settle down to their stationary distribution, makes it work. And there's also, of course, also work to sort of extend this beyond this case, but that's a very important key case. The KPD theorem says something sort of in the converse direction. It says if a system is abstractable in this sense, so this is a very good sort of information theoretic sense, right? When does it have a high level summary, high dimensional summary? When you have all this data, what is the summary I can make? Then it has to be of exponential family form. So yeah, this is really an incredible theorem if you sort of think about it from this sort of more this philosophical perspective.
Well, it's
yeah.
Maybe there's a strengthening of it, but as it stands, it doesn't apply if the sort of if the distribution is not determined by a finite list of numbers, right? So, for example, the kind of exponential family that we're studying in SLT associated to neural networks is not determined by the mean. Is not a number. It's kind of a function, right? The mean varies with the input. So I don't know if there's a generalization of KPD that applies there, but as it stands, it's not obvious to me that this is actually relevant to the kind of problems you would, if you're modeling the real world by things that are conditional probability distributions, then it's not so clear to me that KPD tells me much about the abstractions that I might care about.
Yeah, so there is so yeah, one of the important theorems that Wenworth proves is a very strong generalization of KPD. I don't understand it enough to sort of reply to your concern. So I'm not sure if it directly says that, but let me first finish this talk. Yeah, we'll definitely let's come into that later. There are other constraints on KPD. I mean, it's usually it's phrased all in terms of like real valued variables on some subset of Rn. Another point is that you can't allow the domain to vary with the parameters. So if you take like a universe, like a distribution on a varying interval, for instance, it doesn't apply. There's a bunch of things where it doesn't literally apply. Yeah, they're right, but just some exceptions, some things to think about. I agree with that. Yeah. So here, well, to get that, so almost all families of distributions you know and love are exponential families: Gaussians, Bernoulli, binomial, multinomial, exponential, geometric, Poisson. Again, geometric. There's a whole list. I think the Cauchy distribution is not exponential. Well, there are a couple like very little obscure distributions that are not exponential. But one important example of that are not exponential families are mixtures of Gaussians, and obviously these are very natural. So natural abstraction must go beyond just sufficient statistics. There's somehow another orthogonal direction that has something to do with clustering and hierarchical structure. So clustering would be like how ML people would think about it, and machine learners would think about it. Anyway, famously, these are these are well known to be singular. So perhaps singular learning theory has something to say about this sort of, let's say, maybe orthogonal is too strong, but this other direction. And this is really speculation, but something about the exceptional divisors being having this sort of intrinsic graph structure, and maybe that's sort of is related to this hierarchical structure, clustering structure. But maybe not. But I defer to your expertise in this. Maybe it's more like a question.
Yeah.
Rather than.
I mean, it seems like an easy exercise to do to study this for just the exponential family determined by, or even just the mean and the variance. Just do the resolution, and I mean the exceptional divisor is easier to think about in that case. So the mixture, yeah, I don't know what you. I mean, that's studied in SLT, but I don't know what. So you're proposing something like, look at the mixture of Gaussians and figure out what the appropriate analog of what KPD is saying, or what sufficient statistics are there. Yeah, it's interesting.
Yeah, maybe it's like you have the singular thing, you blow it up, and then you get a bunch of smooth varying families. Like if I have a mixture of Gaussians, do I blow it up and I get a bunch of pure Gaussians or something that are sort of
there's an obvious
structured or clustered?
You could say the way you think about a mixture of Gaussians, the way you write it down is you kind of have already presented it in terms of the mean and variance of the two Gaussians and the proportion in which you mix them. So I guess the question is, you could see the theory of sufficient statistics and the KPD theorem as saying that, well, there's many ways of seeing that the mean and variance are kind of central quantities. They're the moments, and you could go to the reconstruction theorems from moments, I guess. But this would be another way of seeing that if you just have this family, the natural parameterization is the mean and variance. I don't know of a similar result that would say, suppose someone gave you a family of distributions which was a mixture of two Gaussians, but they didn't tell you that. It's just you had to look at various quantities to do with these distributions and somehow see that this is the natural parameterization. How would you extract this parameterization in some natural way? That's a good question. Yeah, I hadn't thought about it.
Yeah, if we think about language data, like a large language model transformer, it feels like part of it, what it's doing is clearly some sufficient statistics, right? It's like you look at these attention heads and they're trying to compress. Well, they're really doing two things, because the attention is also very important. It's like, okay, I can say more about that, but let's it's clear that part of what it's doing is the sufficient statistics story, where it's trying to compress a fairly large data sample with lots of bits, right? Like a context window can have lots and lots of bits. Well, one attention head only concentrates on part of that context head, but then a context window, but then it still compresses that. But there's also clearly some more hierarchical structure going on. That's clear in how I don't know if you think about Chomsky grammars or something like that. Language is hierarchically structured. And in GPT, in the transformer, you have these sort of layers of I don't know how they're called, but basically layers where something gets compressed, it gets fed to the next layer, and then this sort of gets processed.
But what's the uniqueness in the KPD theorem? It says there exists sufficient statistics, but there's no hint of, for example, the mean and variance are sufficient statistics. But from the formula, I suppose you could. It doesn't seem without thinking about it further, it isn't obvious that the only sufficient statistics are like a change of basis, somehow like related to the mean and variance by some simple, so that you can't do anything He doesn't seem to rule out the possibility that there's two sufficient statistics, the usual one and some exotic one, which is just as good but isn't really, the same idea as the old one.
Yeah. No, yeah, that's a good observation. There's also this thing about minimal sufficient statistics, like which is not quite what you're talking about, but usually you want to have minimal sufficient statistics, not just sufficient statistics, meaning any other sufficient statistic is going to be a function of the minimal sufficient statistic. So yeah, that's what people often study. And maybe if you have two minimal sufficient statistics, they have to be functions of each other. Maybe you can then sort of argue that they have to be inverses. Well,
yeah, I think if there's a notion of minimal sufficient statistics, then probably that answers my question, because the minimal ones are probably something close to unique.
Yeah. Well, I think there are also examples where there's no minimal one. Okay. Yeah.
Cool.
So yeah. So there.
Do you mind if I hijack your board and write up some questions to think about later?
Yes. Great. Wonderful. Yeah. I think yeah. Go for it.
You can continue speaking. I'll just jot down the ones that we.
I see. Okay. So Wentworth generalizes in three directions. This KPD theorem in three directions, and I'm not sure if it really answers your question about the issue of abstractions in neural networks, but I think it's a big generalization in any case. The first one is not necessarily IID samples, so that's just a minor thing, but I think it also, in singular information geometry, there is a way to go beyond IID samples, and I think I talked with Edmund, and he said it was not such a big jump, but anyway. The second okay, well, let me talk about the other one is the BaseNet. You don't want to just apply this to a distribution. You want to start with an actual causal model. And well, yeah, maybe there's some background that sort of John Wentworth sees everything in terms of these giant causal models or BaseNets. And now you would like a similar theorem where you say something about all these like a whole collection of variables that have some causal structure on them. And the statement is going to be similar, that you'll still have a fixed dimensional sufficient statistic, that it exists if and only if the distribution is exponential up to a exponentially small set of exception variables. So there's some small set of variables that are not exponential form, but they form a smaller and smaller part of the whole system. And I think the intuition here is something like the telephone theorem, which I would have maybe talked about if I had realized I had a bunch more time. So maybe you've heard about the telephone game. You sit around a circle. One person starts with a word, and they whisper to the next person, and it sort of passes around. And as you might know, then if you go around, then the original world gets completely garbled. So there's this slight noise, and if you multiply that a lot, it will completely decohere the message. Approximately, because if you only have noise that sort of flips the letters, then if you start with a, let's say, 7-letter word, then if you only flip the letters, then at the end it will still have the 7 letters. So there's these constraints that do get preserved even through arbitrary noise, and that's sort of the part of this story, is that when you have these variables that are far away in this in a physical system, then sort of noise wipes out everything except for these sort of intrinsic constraints, and they don't necessarily have to be. Usually they're deterministic, but they don't have to necessarily be deterministic. Yeah, I think the story is at least that these should be part of these abstractions, but
I'm sure
but
Ben is
I don't
seeing
think
that. I mean, what you just described in physics, he would talk about the correlation function between observables at 2 locations, and often that falls off exponentially. Typically, it's e to the minus something.
right.
So, but it's,
right.
I find it like it's not so simple as that. Just like, I mean, what I hear you saying is something like, you would expect that the correlation is somehow a function of these higher level statistics if you go far enough away, and that might be true, but long range interactions can be very strong in relation to noise. There's not. It depends on the system. So. So conformal field theory is, for example, in some sense, a study of exactly what happens when it is exactly possible for a system at a critical point to have long-range correlations that are much, much stronger than noise. And then you could say, maybe that's another way of saying the same thing, though, right? It's like, well, okay, then we know that at the critical point, maybe it's in some universality class, and maybe there's some connection between the nature of that universality class and the sufficient statistics, which are these things that you want to say govern the long-range correlations.
Yeah. Thanks for that. That's super interesting. When I asked John about, like, it sort of suggested in the post that this is the case, but when I asked him, he's like, oh no. But that is interesting. I mean, I'd be wondering what you think of this story. Maybe you've heard this phrase, edge of chaos.
I don't know about chaos,
which was sort of popular in the 80s, or there's something like, well, the systems that we find are interesting, like the brain or life or something, they're sort of in this Goldilocks zone between like complete chaos or like very simple very simple stuff, simple interactions.
They're often at critical points. Yeah, I mean, this is
that's, I guess, what I was trying to get at. Yeah,
there's a large neuroscience literature on this. Yeah, that's what I know what you're referring to. Yeah, it makes sense. It's almost the only way we know of coordinating systems across multiple scales, which characterizes most living systems above a certain level of complexity. And most organizations and many systems we observe in nature have this coordination across scales, and almost wherever we see that, it takes the form of things poised at critical points, just because that's how there's no other way of amplifying small signals at one scale. Like, there's a very few ways in nature of amplifying a signal at scale n to get a signal that's measurable at scale n+1, and being at a critical point is the canonical one.
Yeah. So it kind of goes around this sort of noise telephone game story. It's like this, oh, you can have some small signal actually propagate or something. It's
Yes, that's
maybe too simplistic, but yeah.
well. I think the idea is simple, but the difficulty is
Yeah.
how to recognize, given your system, which parts actually are the are the things that propagate
Yeah,
from
yeah.
level n to n plus one, and
Right.
that's what the study of universality classes and so on is about.
So will these typically have actual propagators? Like if I think about the brain, it has all basically the long range neuron connections where they send waves, uh, uh, and then there are also like brain waves on like a more global level. Um, is that something that is typical or typical of a class of these? What are these called? This something transition points out.
Yeah, I mean, usually what would happen is something like you'll get your system to a critical point, and
Critical point. There we go.
and then there will be emergent quasi-particles which represent deviations away from the critical point. So in a lattice, I mean, perhaps the simplest example is to take a crystal lattice. Maybe that's not a good example. If you take a spin system and then you deviations away from some critical point will what are they called? Magnons.
But there's some sort of pseudo particles, or
they're. It's been a while since I thought about this, so I won't probably give a. Yeah, the easier example of a quasi-particle of this form, a Goldstone boson, is phonons in a crystal lattice. But I don't think this is. I don't think you should think of this as a system at a critical point. So it's not a good example. But yeah, I don't know how to think about long-range brain waves as being something analogous to a Goldstone boson, but I'm sure there's enough mathematical physicists that have gone into neuroscience that if I Googled for long-range brainwave Goldstone boson, I'm sure.
Right. Okay.
Yeah, let me do that on my phone right now.
Right.
I bet you there's a paper.
Right. But okay, maybe it's a little. Anyway, yeah, I think this was my talk. I didn't prepare that many slides, but I think it was just right.
Here we go. Dissipation and spontaneous symmetry breaking in brain dynamics. With boson modes. Yeah, there's a lot of quack potty papers on this topic, it seems.
Yeah. I can imagine, yeah.
Interesting. Yeah, I mean, it's kind of like anybody with a physics background will look at these kinds of things in the brain and say things like the thing I just said, and it sounds pseudo deep, so you can publish papers on it, but it's like actually has very little predictive power, and actually is like, I don't know, I don't feel impressed by it at all. It's a lot of physicists often go to other areas and do things like this, which makes them feel important and makes the other people feel intimidated, but it's like actually very low explanatory power, a lot of these statements that are physics inspired say about the brain. It could be the beginning of actually a valuable point of view or a platform for understanding what's going on, but in and of itself, it's just actually, when you understand what it's saying, it boils down to not saying very much, really.
I guess my guess is that something like this is true, but it's like one or two probably an order of magnitude or two, like more complex than whatever they're trying, and therefore whatever they're trying is sort of, becomes fairly vacuous or something.
Yeah, I think if you really push that program forward and did a lot of hard work, you could find something useful out of it. But usually people will be content to say the rather superficial thing and find some preliminary evidence for it, and then they maybe move on.
Right.
I could be wrong.
Right.
Maybe this exact topic we just discussed, I did try and actually find interesting papers on this topic a couple of years ago and didn't find much. Yeah, but thanks for the talk.
Okay.
That was really interesting. Yeah, I think we should dig further into the KPD theorem, maybe go through the proof. I'm not volunteering you to give it, but maybe I'll make Ben's here. The new convention at MetaUni is if you jump on someone's head, you've obligated them to give a talk. So,
but also like interested to see like maybe doing resolutions blow up on a mixture model, see if it does anything. Anything.
That one we can definitely do. Yeah. I think it's